Hello everyone, this is Amit Brambhat, your lecturer for CSC 208 at Laurel Ridge Community College. Today we are going to continue on our lecture series on greatest common division, divisors, and other mathematical concepts that will be useful to you in discrete mathematics class. So continuing on with GCD or greatest common division of middle elements, we see a table here. Let's explore a more advanced number theoretical property regarding the greatest common divisor, the middle elements of prime rows. If we examine rows where the index is n is prime, the GCD of the central elements is highly structured. For prime elements for rows like 7 and 13, the GCD of middle binomial coefficient is directly divisible by row prime itself. This is because prime number p cannot be cancelled out by any factor in denominator and combination formula, leaving it as guaranteed factor of overall value. Centerline parity. Let's look at the central column of Pascal's triangle. The central binomial coefficients, there is a distinct difference in behavior between even and odd rows. For even index rows, there is a single unique middle number, and it's always an even integer, excluding the top one. For odd index rows, there are two identical middle numbers, and they are not always even. For example, the middle entries of rows 3, 7, and 15 are odd. This parity behavior is deeply connected to binary representation of integers. Multiset identity proof. Let's prove a fascinating multiset identity. N multi-choose k equals to k plus 1 multi-choose n minus 1. This looks counterintuitive algebraically, but it has a beautiful combinatorial proof using stars and bars. Remember to choose a multiset of size k. From n categories, we arrange k stars and n minus 1 bars. What if we simply swap the rows of stars and bars? If we treat the bars as our chosen items and the stars as our dividers, we are now choosing n minus 1 items from k minus 1 categories. Because the physical arrangement of the symbols remain identical, the count must be equal. GCD first two elements. Let's analyze another simple GCD property, the greatest common divisor of row index n and its first internal entry, n choose 2. If n is an odd number, the GCD is always equal to n. For example, in row 9, the first internal entry is 36, and the GCD of 9 and 36 is 9. However, if n is even, the GCD is always n over 2. In row 10, the first internal entry is 45, and the GCD of 10 is and 45 is 5. This straightforward bifurcation is useful shortcut when simplifying fractional combinations. Non-homogeneous lists. Up to now, we have assumed that every slot in a list is chosen from the same set of options. But in non-homogeneous lists, each position draws from a completely different domain. Consider designing a password that must consist of 2 uppercase letters followed by 4 digits. The number of choices for the first 2 slots is 26, and for the last 4 slots is 10. By the product rule, the total number of unique passwords we can generate is 26 squared times 10 to the fourth, which equals to 6,760,000 possibilities. Identifying when a selection is non-homogeneous is key to security analysis. Permutations for small n. To build intuition for bijections, it helps to explicitly write out all permutations for small values of n. For a set of containing only the element 1, we have 1 factorial, which is one permutation, just one. For the set 1, 2, we have 2 factorials, yielding 2 permutations, 1, 2, and 2, 1. For the set 1, 2, 3, we have 6 permutations. By manually listing those, we can easily verify properties like derangements. In the n equals 3 list, only 2, 3, 1 and 3, 1, 2 are derangements, verifying that subfactorial 3 equals 2. Now, let's move on to next slide, primality test diagonals. Let's clarify common misconception about diagonals of Pascal's triangle. While the rows exhibit fascinating prime divisibility, the diagonal represents specific geometric sequences, not primes. The first diagonal is trivial, consisting entirely of ones. The second diagonal consists of natural counting numbers. The third diagonal yields the triangle numbers. And the fourth gives us tetrahedral numbers. This geometric layout organizes partial dimensions, where each diagonal represents a step up in dimensional geometry. Binomial expansion is where Pascal triangle meets high school algebra. When we expand the expression x plus y raised to the n, the coefficients of the terms match the entries of row n of the triangle. For instance, expanding x plus 1 cubed gives us coefficient of 1, 3, 3, and 1. Expanding to fourth power gives us 1, 4, 6, 4, and 1. Now, notice how the exponents of x decreases while exponents of y increases, but their sum always equals n. The triangle provides an instant shortcut to expanding complex polynomials. Falling factorials. When we build a list of length k from n options without allowing repetition, we calculate the result using falling factorials. This is denoted as n to the falling k. For example, if you want to create 3-digit area code using unique digits, you have 10 choices for the first digit, 9 for the second, and 8 for the third, giving 10 times 9 times 8, which is 720. Falling factorials are mathematical bridge between unrestricted lists n to the k and strict bijections n factorial. Subfactorial formulas. Let's revisit derangements to look at the surprising non-recursive formula for subfactorial n. It turns out that subfactorial n can be calculated by dividing n factorial by the constant e and then rounding to the nearest integer. This elegant formula highlights the unexpected appearance of Euler's constant e in pure discrete counting. It also confirms that roughly 63.2% of all random permutations will have at least one fixed point, leaving 36.8% as complete derangements. Combinatorial identities. Many algebraic equations are actually multiset problems in disguise. Consider the equation x1 plus x2 plus all the way to xn equals k, where we want to find number of non-negative integer solutions. We can think of this as distributing k identical units of value among n distinct variables. This is the exact setup for stars and bars. The number of unique solutions is precisely equal to our multi-choose formula, showing how algebraic equation solving is fundamentally tied to multiset selection. Weak compositions. In combinatorics, distributing k items into n categories is referred to as finding a composition. A weak composition allows some categories to receive 0 items, which corresponds directly to our non-negative multi-choose formula. Conversely, a strong composition requires that every single category must receive at least 1 item. We can easily solve strong compositions by pre-distributing 1 item to each of the n categories, and then distributing the remaining items using a standard weak multi-choose formula. Multiset heads problem. Let's practice with another real-world multiset problem. Suppose a shop sells hats in 5 different colors, and you want to purchase exactly 3 hats. Here, the number of categories n is 5, and the number of selections is k is 3. Since we can choose multiple hats of the same color and order of purchase doesn't matter, this is a multiset problem. Applying a formula, we calculate 5 plus 3 minus 1, choose 3, which simplifies to 7 choose 3. Evaluating factorial reveals that there are exactly 35 unique color combination of hats you can buy. Book arrangement puzzle. Let's tackle this classic advanced puzzle. You have 11 biography books, 8 mystery books, and you want to arrange them on a shelf such that no 2 mystery books are adjacent. To solve this, first we place 11 biographies, creating 12 available slots, including the ends, where mysteries can be safely placed. Slot, biography, slot, and so on. To ensure no 2 mysteries touch, we simply need to choose 8 of these 12 slots to place our 8 mystery books. The number of ways to do this is 12 choose 8, which equals to 495. Subsets table, small n. Let's look at this complete table of subsets for small values of n. For an empty subset, we have raised 2 raised to the 0, which is one subset, the empty set itself. For a set of size 1, we have 2 subsets. For a set of size 3, we have 8 unique subsets, ranging from empty set to the full set. Notice how every subset can be written as a unique combination of elements. This visual table reinforces how exponential growth builds systematically from simple binary decisions. And that brings us to the end of our lecture today on multisets and counting structures. Today we built complete toolkit for discrete counting, moving from basic permutations and combinations to the flexible world of multisets and deep geometric patterns of Pascal's triangle. Whether you are dividing resources into an algorithm or analyzing statistical properties and probabilities, these discrete structures are the primary mathematical language that you'll use. Thank you for your time and patience. And now, if you have any questions, you know how to reach me, email me, or message me. and I can help you answer questions you may have. Okay, take care. Thank you.